Well, thank you. Thank you for the introduction. Thanks, everybody, for being here, listening to me. I will start this talk by showing this map of the Santa Ynez Mountains and all the wildfires we have had in here. And if you live in this area for a while, you probably have seen at least one of those fires. And what did they have in common? Well, all those fires propagate, spread in the direction of communities by downslope windstorms, those windstorms that happen on the southern slopes of the Santa Ynez Mountains. We call them Sundowners, or Sundowner winds. And why Sundowners? Well, Sundowners got this name because it tends to intensify after sunset, and they are strong and gusty throughout the night. And they cause significant drop in humidity and rise in temperature. So you see the challenge during wildfires. And wildfires, obviously, I don't have to convince you, are a major problem, right? Economic, social, psychological problem, right? And so this is just some of the images of previous wildfires that happen in our region, which are costly to fight, costly to our lives, to our health, and everything. We all know that, right? So if you ask a firefighter, what are the wildfire drivers? He will respond, look at the fire triangle. What's a fire triangle? It says, well, we need fuel, need something to burn. Topography is important. Canyons, valleys, mountains are important. And weather. Weather means wind, temperature, humidity, stability. So Santa Barbara got it all, right? And that explains why we are so vulnerable. But what's so unique about Santa Barbara? Well, first of all, you have the Santa Ynez Mountains that runs east-west. The Santa Ynez Mountains block the cool air from the ocean, from the Santa Ynez Valley, that has this V shape because of the San Rafael Mountains upstream, that also interacts with the cold ocean. And then this image also shows this variability where you can see the cool Pacific Ocean, and then the Santa Ynez Valley, the San Rafael Mountains, and all that in a very short distance, right? So you have this this climate, regional climate, that's so dramatically changed from point to point. And if you want to understand Sundowners and also or any other type of a downslope windstorms, you have to look at this river. So what do you see here? You see this fast-moving water coming down. It encounters this rock, accelerates down, and on this side it splashes and makes a lot of turbulence on this side of the rocks. And then if you look at this other image, you're going to see that where you have some cracks on the rocks, right? That water will flow quickly and a lot of turbulence. And we see many of those cracks around. This is the Santa Ynez Mountains with canyons, valleys, and gullies that mimic those cracks. Now you get the point, right? This is a very difficult thing to predict, to understand the variability. And also to forecast, right? But I created this image to try to explain this a little better for you. So imagine this is the Santa Ynez Mountains, the San Rafael Mountains. You have the valley, the coast, the ocean, right? And this is daytime. And during daytime, you have the warming of the valley and the coast. And then you have, we say it's more unstable air. And then at the top of this air, we have a temperature inversion, which makes this like a lid that separates the boundary layer, called this boundary layer, from the free atmosphere. And also the mountains warm, and then the coast warm, and then we have local circulations, like a sea breeze, a mountain breeze, upstream, up mountains. This is the normal circulation anywhere you have mountains. During the night, what happens? It cools down very fast in our region, and then this boundary layer shrinks, collapses, and stability increases. And then you have the reversal of the winds. So cold air comes downward and both sides of the mountains, and even kind of faces the ocean, against the ocean circulation. When you have sundowners, what happens? Then you have this very fast flow aloft. And then we have our analog, hydraulic analog, right? Have this very fast winds aloft, encounter the mountains, and come down like we saw in the images in the video, come down very fast. This is our sundowner. We call this lee jet. Have a lot of turbulence on this side, both mountains, by the way, but Santa Ynez tend to have stronger winds. And at the valley, if you live in the valley, you may even not notice there is a sundowner going on over there, right? So, in other words, in summary, what is sundowner? We have a fast flow coming, encounters the mountains, accelerates down the mountain. This is our sundowner. On the other side, jumps. You see wave breaking, turbulence developing. We can see this again. This is an image of the Wildfire fire. We are looking west towards the Gaviota area. And then we can see the laminar flow, right, becoming very turbulent on the other side, jumping. So that story that I just told you, we can see when we have fires. So we can see also, this is another image showing during the tea fire, that we had these very strong sundowners and also the hydraulic jump, as you can see here. And you see these ups and downs, ups and downs, ups and downs. So these ups and downs are what create conditions, because every time you have up, you have conditions for the fire to take the embers up and then take them ahead of the fire line. This is what happens in most fires when we see, like we saw during the LA fires, right? The fire started in the mountains and ended up close to the coast. So that's the challenge that we are talking about, that we want to understand, that we want to forecast, and want to improve our resilience by improving forecast of all these issues I'm telling you. But there is another thing important. When you have a sundowner or any kind of downslope windstorm, so if you imagine this is the atmosphere with pressure increasing as you get closer to the surface, we see if you force air coming down, it will be compressed and will warm. Will warm, and then relative humidity will decrease, right? This warms pretty fast. And then we say it's adiabatic warming. So when we have, if you think about the mountains in Montecito area, if you take air from the top of that mountain in Montecito all the way down, we see the total temperature may increase 17 Fahrenheit from top to bottom. So you see the importance of this process, just due to this process. And also, what happens when you have mountain waves and hydraulic jump, you can have a lot of turbulence, or even rotors, which is the reverse of the winds. When this happens, well, we have a lot of turbulence that is risky for aviation as well, right? Because it's a fast change in wind direction. And you can also see the intrusion of the marine air due to this process. So, I want to say something important, because people may think that, oh, sundowners are the same as Santa Ynez winds. No, they are not. They are very different. This image is showing just an example during the Thomas fire that was ignited during a very strong Santa Ynez wind. And Santa Ynez are more of an easterly type of winds. In Santa Barbara, we barely get any winds when we get Santa Ynez winds. However, a few days later, we had conditions for sundowners to form, and then you see the wind direction changed. This is when the fire jumped to Santa Barbara, and have more northerly winds, northeasterly winds in this case, on this side of the frame. And what drives those events? Very different synoptic settings. So you have for Santa Ynez, high pressure system on the high plains of the US, low pressure system off the coast. For sundowners, notice this is very different. It's actually tend to have low pressure system in this area over here, right? And you have two types of sundowner winds that I'm going to explain a little later. So depending how this high pressure system is, the low, we always have low pressure system near the coast. That's important for sundowners as well, the low pressure on the Santa Barbara channel. And the National Weather Service even used this proxy to say, okay, when they have differences in pressure between Santa Barbara and Bakersfield Airport, you have type of eastern sundowner. When you have Santa Maria Airport and Santa Barbara, differences in pressure, we have western sundowners. Santa Ynez, very different. The time of the year, very different. Santa Ynez are in winter, sundowners in spring. That's the peak of the season of those winds. What do we do now to study these winds? Well, first of all, we investigate sundowners or these winds using complex models that they have dynamical equations and physical equations to reproduce the behavior of those winds. We also do downscaling from coarser resolution, reanalysis we call, to 1 kilometer resolution, which is important to understand all this complexity. And then we now are performing experiments at very high resolution, 100 to 40 meters, to try to understand all this complexity of turbulence that I explained to you. This is an example of one of these results using model, in this case, 2 kilometer resolution. And what we can see, arrows are showing wind, right, where winds are coming from, and colors are showing relative humidity. So the first thing that probably caught your eyes is that, well, winds vary along this area in direction even. This is during the Painted Cave fire. This was June. And relative humidity also varies a lot. So you can see it's not just, oh, we have sundowners, everything will be equal. No, you have a lot of variability in relative humidity and in wind direction. In this case, you have more of northwesterly winds. This is the case of the Resuscita fire, another major fire in our region. And you can see that this was about 6 p.m. By that time, we had stronger northwesterly winds and northeasterly winds in Montecito area, and basically no winds here where we are, which is normal the case. We barely get very strong winds here at UCSB. So, but this shows you how complex forecasting these winds are. And color relative humidity is obviously much lower during the Painted Cave fire than during the Resuscita fire. So you see these differences. We found that we have 3 types of sundowner winds. The first one is the western sundowner that typically affects more the Gaviota area. We have the eastern sundowners that are more important in Montecito, typically affect Montecito. And you have a hybrid when you have both regimes, which is the most challenged in case we have a fire, as you can imagine. What do you do to improve forecasts? Well, we have been collaborating for many years with the National Weather Service that do the forecast for our region. And then we provide them a daily 84 hours forecast so they can use those forecasts. We provide tools for them to analyze those forecasts. And we have also working on different things like machine learning. Professor Charles Jones is doing this machine learning to improve wind and temperature representation, much higher resolution. We do research to improve forecasts. We're trying to improve this forecast in 5-7 days, which would help them to improve their own forecast. And we put all that available in our website. So this is an important thing we are doing, I think. But we don't only do models, right? We are also interested in observations. And in 2022, we were very, I would say, perseverance played a role. We had this Sundowner winds experiment, which happened between April 1st and May 15th, 2022. And it was a joint project of 10 institutions. We had the support of the National Weather Service, of the Forest Service, of the Fire Department, Montecito, and Santa Barbara Fire Department. And this was a major thing for us here. And so this project brought many instruments, the most sophisticated instruments to measure the boundary layer, the lower layer of the atmosphere and the winds. All these symbols here are instruments that were installed for these 45 days in here. I'm just showing a few instruments. I'm not going to go into details, but just to show how sophisticated those things, instrumentation were. We had aircraft. This is showing also the flux tower that we installed in one of these places. So we had 17 flux towers like this with all these sophisticated instruments and placed on the most incredible, difficult places in the mountains here in Santa Barbara. And we also had aircraft in this region flying across the area through 13 missions. Those aircrafts, they had lidars. Lidars are laser, right? They point down, and the laser responds to aerosols and backscattering of that aerosols. You can convert the signal into data as temperature, humidity, and so on. So they also had drop zones. They were dropping zones and measuring profiles of temperature and moisture through the atmosphere. And we also had folks driving cars and collecting data as they were driving. And there was also another LiDAR in this truck that was driving across all the roads we have and the freeway and collecting data as it was driving. So we had all possible sophisticated instrumentation to study Sundowner during this period. We had also radio sounds that were launched. Those are sounds that go up with the balloon. And we had students. Too bad we were not here by then. It was super fun. They had to launch every 3 hours in the night. They were amazing doing this job, launching balloons every 3 hours during the nights when we had Sundowner. You can see here how strong the winds were when they were trying to launch balloons. And we had this in 4 sites. And now I'm going to finish by showing some of the main results, and I picked the ones that are aircraft driven to impress you. So this is a picture of the aircraft crossing the mountains. And now I'm going to convince you that all that theory actually works for Santa Barbara and is even more interesting. So in this case, the aircraft was flying from the Santa Barbara Channel across the Santa Ynez, across Montecito, the mountains in Montecito, right? So you're seeing, when you look at this, imagine you are flying from the coast to Montecito. And what do you see here? So on the top is potential temperature. You can think this is temperature. And look at those lines, how they go up and down, up and down. Oh, those are the mountain winds we are talking about, right? And these lines, when they get very close together, this is the inversion I was talking to you, that creates this lid that separates what's happening up with what's happening close to the surface. And you can see warm and cold, warm and cold, warm and cold. See, the waves actually exist as they exist in the ocean, and they perturb temperature. And you see that below, if you are in this area close to the coast and foothills, that particular hour, this was at 20 PDT, you basically were feeling the marine layer. See how cool this was. Just cold, just the marine air in this area. You wouldn't say, oh, just a nice breeze day. You don't have to worry about it. But if you are a little bit up, then you start seeing a lot more action. And the other thing that's interesting, See how dry this air can be. This is as dry as it could be in terms of general dryness this particular day. So you see this is dry, getting a little more moisture from the ocean as you move close to the coast. And you see it moves with the mountain waves. But we did have winds. The winds were coming from north, right? We had conditions for Sundowners that day. So by midnight, by midnight, the mountain wave, you see, remember, mountain waves have to do also with turbulence. That turbulence mixed things up, right? And then this mountain wave basically touched ground. So of the warm, not as warm as here, but you see some warming also affecting the lower elevations of the Santa Ynez Mountains, the foothills. And the winds, this was the time when the winds were the strongest on these slopes. And then the ocean, the air of the ocean was still cold, and you can think of a tug of war, you know, between the air from the ocean and the air from land. And this is what happens. All the time when we have Sundowners, we never know who's going to win, the ocean air or the Sundowner air coming from the mountains. And this matters a lot when you have a fire. And so we see this dry and moist air, these contrasts in here, the sharp contrasts we see in moisture. The other interesting thing was observed by the mobile LiDAR that was installed at the truck, as I told you. So they drive all over the place around, and I'm showing one date when he drove from Gaviota to Golida area and collected observations as it was driving. And it's looking up, and the LiDAR is measuring winds, can measure up to 1,500 meters. This is meters, okay? And then what do you see that? I find this to be fascinating because you can see how shallow. First of all, this was a Sundowner, western Sundowner, very shallow, very close to ground level. You see all this intensification of winds. Some pockets of winds, yes, when we are driving, we see that. As you pass through the cracks I was talking about, remember the cracks that I showed with the current? You see the winds intensifying on these locations. But what is amazing is that at some point, you get nothing. Just light winds with different direction. So that's the biggest challenge. When you imagine that now you have a fire like Alisol that happened on the western portion of the mountains, and you have to evacuate people, right? How far are you evacuating? Because you may not need to ask these people to evacuate, right? You have more to concern about people living here, or maybe at this neighborhood, or should I evacuate everyone all the way to that point? So having a better understanding, a better forecasting, comparing models against observations will help us to understand, well, can we rely on models? What do we need to improve this, right? That's the benefit of having an experiment the size of what we have. We are still working on the data sets. We have seen different things. The model can and cannot, sometimes can, sometimes cannot, mostly cannot if you don't have the right resolution. Meaning that if you use very coarse 1 kilometer, 2 kilometers, you may not see all these cracks, all these things that are important in turbulence and during wildfires. But we are getting there because understanding where we failed help us to improve what needs to be improved. And so with this, I will end with a Sundowner in a nutshell, saying, well, what are Sundowner? They are gusty offshore winds from the Santa Ynez Mountains. They occur year-round. They're more frequent during spring. They pick up late afternoon to early evening, tend to end early morning, generally. We have mountain waves that bring compressional warming and drying of the atmosphere. This is the most important point. There are 3 sundowner regimes that we know: the western, the eastern. They affect more Montecito and Santa Barbara, western Gaviota, Refugio area. And then can have cases where they are strong across the mountains or just strong in Montecito and Gaviota areas. And they drive all major wildfires in Santa Barbara. We had one recently in Refugio. We didn't have any wind, basically, here, but in Refugio area, you're having sundowners, and then during a recent fire, right? But the marine layer came and then cooled down things and helped in fighting this fire. So with this, I finished my presentation. I also want to thank everyone that has been helping with this work. This is a big team, as you can see. All my graduate students and postdocs and scientists involved in this research. And we continue trying to improve this because we want to create a framework that will protect us, because with a better forecast, we will mitigate and prevent major disasters in our region, right? And this is my talk today.